Hi, so for today we're going to talk about three-dimensional force system, equilibrium, still a part of statics of rigid bodies. But before that, bati muna tayo kay Shahani Mapantas, Christian John Ariola, kay Riz Dowell Rosmilla or Rosimilia, and kay Lloyd Seprado from University of Mindanao. They are all civil engineering. Hi sa inyo. So, happy watching and enjoy watching. And sila din po pala yung group ng students. They call their team as Team Abat. So, salamat. And then, meron din tayo si Maria Keisha, GMB Saison, BS in Agricultural and Biosystem Engineering from Bicol University, College of Agriculture and Forestry. So, hello sa inyo and enjoy watching. So, thank you sa pagtangkilik sa ating channel. So, going back to our study, so we shall be talking about three-dimensional force system equilibrium, statics of rigid bodies. So, on our previous video, we talked about two-dimensional. So, the condition for equilibrium, again, is still the same for 3D, wherein we have summation of forces along x equals 0, summation of forces along y equals 0, and summation of forces along z equals 0. So, we are dealing with three-dimensional. So, we have x-axis, y-axis, and z-axis. So, the conditions are still the same. Okay, that the summation of all the forces acting on that particle should be equal to 0. So for number one example, okay, we shall try this. A 90-pound load is suspended from the hook, shown in the figure below. If the load is supported by two cables, that's cable here, and this cable, and a spring, so we have a spring and a cable, spring having a stiffness of K equals 500 pound per foot. Okay, determine the force in the cables, the forces in the cables, and the stretch of the spring. This spring, okay, for equilibrium. The cable AD lies in the XY plane. Here's our X plane, Y plane, and Z plane. So this cable lies on the X and Y plane, and cable AC in the X and Z. So we need to find the again the force in the cable AC, AD, and then the stretch of this spring due to this load, 90-pound load. So here is our image, our given. If we are going to draw the free body diagram or FBD of this problem, we have this FBD, wherein we have a reference in the point A, where all the forces meet. Okay, so again, we're going to sum all the forces acting along X, Y, and Z, so that we would be able to get the tension in each cable and as well as the stretch of the spring. So we label this as, in this AC, that's the tension F sub C, okay, force F sub C, and then we have F sub D, and then we have F sub B due to the spring, okay, and then we have the weight, 90 pounds. Okay, so let's start with the summation of forces along X. So obviously this spring does not have any X component because it's purely on the Y. Same as this weight, it's purely on the Z. So it's given in our problem that cable AD lies in the XY plane and AC lies in the XZ plane. So both cable AD, this F sub D, force F sub D, and force F sub C has an X component. So first we start off by writing the equation. Again, this is our positive X. Okay, this is our negative X, considering this point A as our origin. This is our positive Y, negative Y, positive Z, and then negative Z. So we need to take note of the direction of the forces, as we will be using that in order for us to get the sign, the correct sign of the forces component. Okay, so summation of f of x equals 0. So let's start with this FD. Okay, the force in FD, tension FD. Okay, so how are we going to get the X component of this? As we all know, this is the X component. And this length is the same as this length. Okay, so we have to get, okay, and this we have 30 degree from the y-axis, negative y-axis angle. So this x is the same as this x. Okay, so what will I do is to find a way in order to express this, resolve this f sub t into its x component. Okay, that I will also use the f sub t. So we can use the sine function given this 30 degrees. So if we write the sine function, I'll just write it. Okay, in case you have forgotten. So we have sine 30 degrees. Okay, since this is x, this is also x. Okay, and what are we going to do is to get sine 30, that would be, okay, opposite. This is uh, a 90-degree angle. This is the hypotenuse. So opposite x all over FD. Okay, so the x component of this vector f sub t should be f sub d sine 30 degrees. So that's the x component. So in the summation of f of x, we start with summation of f of x again. Okay, we have f sub d sine 30 degrees. And it's positive. Why? Because if we resolve this vector here in the x-axis, it's in the positive direction. So we have a positive. Okay, so how about f sub c? As you can see here, we have f sub c. This is our negative x-axis. We're going to project this f sub c on the negative x-axis. So if we project this, okay, considering that we have an angle here, included angle, oops, let me just remove that. Okay, so we have the triangle, we have the 5, 4, and 3. So in order for us to project this f sub c on the negative x-axis, we're going to use what? We have to involve 4, okay, and 5. And what function would involve 4 and 5? That's cosine. So instead of using cosine theta, if we get the cosine theta, that would be automatically equal to 4 over 5. Okay? So if you did not get what I'm trying to say, we have this figure, okay, wherein this is our 5, this is our 4, and this is our 3. Okay, this 4, okay, this 4 is the same as the direction of x. So given that this is the angle, for example, okay, we need to get a trigonometric function that involves this 4 and this 5. And what is that? That is the cosine theta. We have adjacent over hypotenuse 4 over 5. So, okay, so that would be minus, because if we project this f sub c, it's here in the negative x-axis. So that is minus. So instead of getting cosine theta, writing cosine theta here, since we don't know the angle, okay, we simply write 4 over 5. So 4 over 5, okay, and again, 4 over 5 of our FC. Okay, this FC. Okay, then that is equal to 0. So that's our first equation for summation of forces along x. So how about summation of forces along y? So same process, okay? Same process. We're going to resolve it. So for the summation of Fy, obviously, if this is sine 30, okay, this should be negative Fd cosine 30 degrees. For this, 1, okay, because we're going to project this f sub t into the y, and here is the y-axis, negative y-axis. So if we project this to this, we're going to use cosine because of, again, the triangle, okay? And what are we going to do is to write negative because if we resolve it, it's going to the left. Okay? So we have negative FD cosine 30. Okay? Any forces other than that, acting along y, okay, is this FB. So it's going to the positive, okay, to the right. So that must be plus f sub b equals 0. And that is our equation. There, the f sub c does not have any y component because it lies on the x and z as well as the weight. So if we are going to get the summation of forces along z, okay, which is should be equal to 0, okay, what are we going to do is first f sub c, okay, we are going to resolve this f sub c on the z axis. Okay, this axis, so we're going to involve 3 and 5 here in the triangle. So given that the angle is here, so we use a while ago cosine. So this one, in order for this 3 and 5 to be involved, we're going to use sine. Okay, and it should be a positive because if we project this f sub c onto the z-axis, it's going upwards. So it should be 3 over, okay, 5 f sub c, okay, the dot force, minus, force, minus, acting along z is the 90, and it's going downwards, so by convention, that's minus 90 equals 0. And that is our equation 3. So, we need to solve fd, f sub c, and f sub d. So, we have 3 unknowns, we have 3 equations, so it's very simple for us to solve. So, from equation 1, okay, we have fd sine 30 degrees equals 4/5 f sub c. Okay, so we can get fd, we can express that in fd, 4/5, you have f sub c divided by sine 30 degrees. Okay? Okay. So, but the problem is we don't know the value of f sub c, and we can get the f sub c from equation 3. Okay, from equation 3, we have 3/5 f sub c equals 90. So, if we get f sub c here, f sub c would be equal to 150 pounds. Okay? And of course, if we know the f sub c, we can get finally the f sub d. That's 4/5 of the 150 pounds all over sine 30 degrees. Make sure you are in the degree mode. So we have f sub d, okay, and that is 240 pounds. Okay, and finally, we can solve for f sub b. Okay, f sub b. F sub b is simply from equation 2. From equation 2, we have f sub b equals fd cosine of 30 degrees. So our f sub d is 240 pounds, and that is multiplied by cosine of 30 degrees. Our f sub b, which is the force existing on the spring, okay, is 208 pounds. And as we all know, the force in a spring, okay, is equals to Ks, wherein S is the stretch. Okay, so we have FB equals Ks, and we are given a K a while ago, that is 500 pound per. Okay, so we need to get S. That's the what we are trying to get. S would be F sub B all over K, and that would be 208 pounds all over 500 pound per foot. And that's the stretch, okay, in the spring. So our S would be 0.416 feet, and that's the stretch in our spring. So this is our answer. So we have the tension, okay, on the cables F sub C and F sub D, and here is the stretch of the spring. Okay, so let's go now to our second example. So we have the 10 kilogram lamp is suspended from 3 equal length cords. So this is the lamp suspended from 3 equal length cords. Determine its smallest vertical distance S here, okay, from the ceiling. This is the ceiling, okay. Smallest vertical distance from the ceiling, okay. If the force developed in any chords C, B, and A is not allowed to exceed 50 newtons. So what we need to get here is the smallest vertical distance from the ceiling so that these chords would not develop exceed 50 newtons. Okay, so the maximum allowable is 50. But once the tension or the forces, okay, tension here in our cables exceed 50 newtons, then it would break. Okay, the maximum allowable is 50. So let us analyze this. So we have a 600 millimeter distance here from the ceiling up to the point C, point B, and point A. And that is, they are all equal, 600 millimeter, 600 millimeter, 600 millimeter. And again, we have equal length chords according to our problem. So that, okay, if we are going to really to analyze this problem, okay, so we have the free body diagram here, okay, and we have an angle gamma here, okay. We have to get the, let us note, okay, that DA, that segment, the length of DA equals the length of DB, okay, equals the length of DC, which is equal to 600 millimeters. Okay. Also, we have to take note that the summation of forces along X would cancel out each other. Why is that so? Because if we analyze this point A, if we project this, that would be the positive Z, and this would be the X. Okay? So you have an X component for A, and you have tension A, and you have Z component for this tension. So with the origin here, a point of reference. So it has this tension A has an X component and a Z component. So both are positive. So in regards to tension C, okay, we can resolve that on the Z axis, which is this, and we have on the Y axis. So that's Y. So it has a positive Y and again a positive Z. How about the B? Okay, tension in B. So it actually involves, okay, X also, okay, as well as the Y, negative Y, okay, and the Z here. So it's positive Z. So the tension B lies on the XYZ plane. So it is now this one is now negative X, and this one, since it's going to the left of the Y, okay, that's negative 1. So if we are going to sum all the summation of forces along X, since they are all of equal length, okay, their forces are all the same. So we have positive X cancelled by positive component of X, okay, of tension A is now cancelled by the X component of the B, okay. So we don't have any forces acting on this on the summation of forces along X would be 0, okay. So no component because they would be cancelled out. So again, the same process in summation of Fy on the y-axis. Why? Because in this case, tension A has no y component. Okay? But tension C has a positive y component and tension B has a negative y component. So since they are equal length, they have the same tension, So the forces component in the y tension of the T sub C and T sub B would cancel. So we have Fy equals 0. Okay? So if we perform summation of f of z, which should be always equal again to 0, okay? So this happens because of the symmetry, okay, if you're going to analyze it. So in f sub z, okay, still it's equal to 0, but we need to write the equation, okay? So considering now the free body diagram here, so we have tension T, tension T, tension T, they are all the same. Why? Because they have equal length and they are symmetrical. And if we're going to have an angle gamma here, okay, and then we have a distance of 600 millimeters from A to D, same with B to D, same with D to C, okay, which are all 600 millimeters. And this gamma is an angle the same with this two tension, okay? And if we are going to resolve, we can see here, okay, in tensions A, B, and C, if we're going to resolve it into our z-axis, they are all positive because it's all going upward into its component. So, in order for us to get the z component, okay, of this one, we need to use the cosine function because this would be our uh, hypotenuse, okay, and we need to involve 600 millimeters in this one, okay, because it's our tension T. So if we're going to use, okay, summation of forces along Z, that would be, can I write 3 because it is for the 3, okay, 3 times the maximum tension, okay, maximum allowable should be 50. So we should, okay, let me just rewrite this. So this would be 3 because all tensions are going upward. Okay, so that would be 50 cosine gamma for A, 50 cosine gamma for B, plus 50 cosine gamma for C. So we make it times 3. Okay, because they are all going upward, which indicates positive. So we have 3 times cosine, okay, 3 times 50 cosine, I mean, okay, that's the maximum tension. We substitute it to our tension, cosine of gamma, okay, minus this weight is 10 times 10 kilogram times 9.81, okay. So we have 10 times 9.81 equals 0. So we need to get this angle, okay, and upon this getting this gamma, we have cosine in arc cosine of 98.1 all over 150. So we need to get that gamma in order for us to get this S, okay, or the vertical, smallest vertical distance from the ceiling, okay, to the lamp here, okay, point of reference here. So we have 49.16 degrees here. And then, of course, if we get this angle, okay, so if you know this angle, so from this triangle again, okay, take note that this side is equal to S. That is equal to S, this side of the triangle. That is also equal to this smallest vertical. So if we know the angle, we can use tangent function, tangent of 49.16 degrees. Tangent, opposite, okay, we have opposite, 600 millimeters, okay, all over adjacent, which is the adjacent side, S, and that is our smallest vertical distance. So we have S equals 600 millimeters all over tangent 49.16 degrees, and that is 519 millimeters. So that's the smallest vertical distance. Okay, let's proceed with the third example. So for the third example, determine the force in each cable D, B, C, okay, cable AB, cable AC, cable AD, used to support the 40-pound, okay, crate shown in the figure below. So we need to determine the forces in each cable. So the previous examples, uh, we are dealing with, let's say, this example, the first example, okay, we are dealing with the angle. We know the triangle here, the length of the triangles. But for this problem, okay, some distances or some parameters are only given, such as the distance from the x-axis, the y-axis or y-axis, okay, and the z-axis. So in order for you to solve for the forces in developed by each cable, we need to use the Cartesian vectors. Okay, still, we don't know the forces. We are going to represent the forces using the Cartesian vectors. So let's try to get F sub B first. So the force F sub B equals the component of FB. I'll write its slant. Okay, this is Cartesian vectors, and that is multiplied by the unit vector in the direction of FB. So we have to write the unit vector of that. So we have in the x-axis, okay? So we're going to get it, represent it in the Cartesian vector form. So to get to this point, we have 3 feet, okay? That is negative 3i, okay? That is a vector, okay? Negative 3i, why negative? Because this is the positive x, this is the negative. Of course, then what do we need to do? We need to what? For the y component, we need to go here, okay, in order for us to reach here. So, and that is equivalent to 4 feet, okay. This one is equivalent to this. So, it's going, okay, if we're going to resolve this, it's going to the negative side of the y-axis, this one. So, this is the negative. So, we have negative 4 units from the y-axis. We have 4j. These are vectors, okay? And then, okay, from here, we're going to go upward so that we reach the B. Okay, and that is 8 feet. So that's positive 8k. And of course, divided by, this is a unit vector, okay, in the direction of FB, okay, the force B. So that must be negative 3 squared plus negative 4 squared plus 8 squared. Okay. So if you haven't watched my video about Cartesian vectors, please watch it so that you can have a recap of what we are trying to do here. So if we are going to evaluate this, okay, our force F sub B would be negative 0.318 F sub B, okay, I minus 0.424, okay, F sub B J, and then we have plus 0.848 F sub B in the K direction. Okay, so here are our Cartesian vectors. So how about for F sub C, still the same process. So if we want to get the force, okay, F sub C here, okay, the vector F sub C, that is multiplied by the scalar component F sub C and by its unit vector in the direction of F sub C. So we have 3 feet, okay, that is still negative 3i, okay, negative 3i. And then we have to get here, that is 4 feet again, okay, but in the direction of the positive y, so that would be plus 4j. So, and then going upward, okay, that is also 8 feet, so we have plus 8k all over, okay, the square root of the sum of the squares of the components. Okay, so if you evaluate this, our vector F sub c would be negative 0.318 F sub c I plus 0.424 F sub c j plus 0.8 0. Oops, 0.848 F sub c k. So how do you get these values? So for I, you need to have negative 3i all over this value. So you get negative 0.318. For j, okay, for the numerator, you only have to retain 4 all over this equation. Then you get 0.424. And for the last one, for the k, you have 8 over the square root of the sum of the squares. So you have these components. Okay, that's our vector f sub c. How about, okay, the force f sub d? For f sub d, okay, we cannot assume, okay, that from point A to point T, that the distance is 3 feet. Okay? We cannot assume that. Okay? Because it's not given. So, but we all know that this cable D, okay, only lies on the x-axis. So, if we're going to get the component of that, that should be the FD, okay, scalar component FD, whatever the force FD, okay, and then in the positive I direction because it is in the positive X. So, and again, the weight, okay, the weight here is also does have a force. We consider this as a force. It's going downward, okay, and we know that this is 40, so that would be negative 40, okay, k, okay, it's going to the negative z-axis, so we have written that as negative 40k. So, what is the condition for equilibrium? The old summation of the forces should equal to 0. Hence, okay, F sub B plus F sub C plus F sub D plus the weight should equal 0. So what are we going to do? We're going to simply add this up. All of that components up. So we have negative 0.318 F sub B I minus 0.424 F sub B, okay, J. Then we have plus 0.848 F sub C K. Then minus 0.318 F sub C I. Okay. Plus 0.424 F sub C J. Plus 0.848 F sub C K. Then we have plus F sub D I. Okay. Minus 40 k equals 0. So we're going to group all the in terms of I, j, and k. So we have negative 0.318 f sub b. Okay. Then we have negative 0.318 f sub c for the I. And then we have plus f sub d in the I direction. That is plus, we have for the j, negative 0.424 f sub b. Okay, and we have for the j plus 0.424, okay, f sub c, and for the j we don't have anything, so that's j hat, okay, or j in the direction of y. And then we have plus for all the k, so 0.848 f sub c. And then we have plus 0.848 f sub c. Then we have minus 40, and that is k equals 0. So we need to solve the forces FB, FC, FD. So according to our equations, so summation of forces along x equals 0. So equation 1 would be negative 0.318 F sub B, this one. minus 0.318 f sub c plus f sub d equals 0. Summation of forces along y, okay, is the second equation in J. So we have negative 0.424 f sub v plus 0.424, oops, yeah, plus 0.424 f sub c equals 0. Lastly, we have summation of forces along J equals 0. Okay, then we have 0.848 f sub c plus 0.848 f sub c minus 40 equals 0. Okay, so this is our equation 1, equation 2, equation 3. So from equation 2, we can see that FB is equal to FC. So we have 0.424 FB equals 0.424 FC. So this would cancel. Technically, FB equals FC. Okay? From equation 2. So from equation 3, we can get either FB or FC since they are equal. So what will happen? 0.848 f sub c plus 0.848. This is f sub c also. Wait, I'm sorry. This should be f sub b. My mistake. Okay? This should be f sub b, not f sub c. Okay? So, again, if we substitute this one to get fc or fb since they are equal, so what we're going to do is to solve for f sub c. So we have 0.848 f sub c plus 0.848 f sub c equals 40. So f sub c would be equal to 40 over twice of 0.848. And if we get that, our f sub c is 23.6 pounds. Okay, 23.6 pounds. And that is also equivalent to our f of b. Okay, so of course, this is also f sub b. And just have a mistake in writing. Okay, so we have f sub b and f sub c equals 23.6 pounds since they are equal. And all we need to find again is the other one, okay, which is, I think that's f sub d. So the f sub d can be found simply, okay, by plugging it in our equation 1. Okay, so in order for you to find that, so transpose this. Okay, so we have twice of 0.318 times 23.6. So twice 0.318. Okay, because 2 times if we transpose this. Okay, or you can solve it since it's not, I don't have enough space here. F sub d would be equal to 15.0, 15 pounds. 15 pounds. Okay, this is 15 pounds. Oops. So that's the answer for FB. So that's the tension in F sub B, F sub C, and F sub D. So, and that's it. So, thank you so much for listening. Okay, I hope you learned something for this tutorial video. And this is your take-home assignment. So, if you have the answer, please comment down below. Okay, I'll be posting the answer. Okay, once I get comments on what is the answer of this in this problem. So, determine the tension in each cord used to support the 100-kilogram crate show. Okay, so for this problem hint, uh, you're going to use all of this angle, 120 degrees, 60 degrees, and 135 degrees. Since the angle is given, okay, so you can use it, okay, with respect to the XYZ. Okay, you can do that. You can apply the knowledge that we have studied a while ago. So you have these parameters given and the angles. Okay. So, and again, thank you so much for listening. If you are new to my channel, please don't forget to subscribe. Again, this is Engineer Abat. Thank you so much for listening, and God bless.